The motive of this video is to have a good understanding of counters and timers. This video is not restricted just to users of Arduino. This video will be useful for anybody who is working with any microcontroller. So let us jump into counters first. What counters actually mean, how they function, a quick review or understanding of counters, and then we will see how counters are used to produce a sawtooth waveform and how do we produce PWM for closed loop action of a DC-DC converter. So this will be the agenda of the video. So first, let us talk about counters. A counter is simply a register, and a register is nothing but flip-flops connected together to form an entity. So when we say flip-flop, each flip-flop is capable of storing one bit of data. Either you can store 0 or 1. So such registers, such flip-flops joined together forms a register. In real time, we nowadays don't have 4-bit counters. This is just for explaining you the concept in a nutshell. In scenario, we use 8-bit counters, 16-bit counters, 32-bit counters, or even 64-bit counters. So for simplicity in explanation and understanding, we are going for a 4-bit counter. The same idea could be extended for 16-bit. So a counter is a register which may initially have, assume all values as 0. My CPU is sending clock signals continuously. Now on one clock signal, when the first clock signal comes, this bit changes to 1. So this bit changes to 1. When the second clock pulse comes, the whole thing changes to 2. By 2 I mean to say binary 2. When the third clock pulse comes in, this changes to 3. And when the fourth clock pulse comes, it is incremented to 4. This is how a counter basically works. With respect to clocks, you will have the bits basically getting incremented. So what is it basically doing? It is just counting the clock pulses. That's the main or abstract idea of a counter register. We call this as counter register. Please make note of this terminology. It is called as counter registers. In some, it will be some microcontrollers may be called as TCNT or something like this. It's basically a counter. It's a counter register. Now, assume that I am keeping on giving clock pulses one after the other, again and again, and assume that my clock frequency is 1 megahertz. When I give a clock of 1 megahertz, what will be the period of my clock pulse? It will be 1 upon 1 megahertz, which will give you 1 microsecond. So this distance between two consecutive rising edges of the clock will be 1 microsecond. So for every microsecond, you will have the value of register being incremented by 1. Now, when you look upon the numbers of this register, it will keep going up until what? Until the point or up to the point when all of these become 1. When all of these become 1, it has to stop there. It can't go further. Right. So for the first clock pulse, it's coming here, second clock pulse is coming here, third clock pulse is coming here, and so on up to 14. And when the 15th clock pulse is complete, you will get a number like this. Basically, it has counted up to 15 because the decimal equivalent of 4 ones is 15. It has counted up to 15. Once it reaches this point, there are two possibilities. Either now it has counted from 0, 1, 2, 3 up to 15. It can have two possibilities. Either it can count back that is from 15 back to 14 to 13 down to 0, or once 15 is reached, when the next clock pulse comes, it can directly jump to 0. Based on this, we have up counter and up down counter. Now first let us talk about up down counter. Assume that I am giving a 16th clock pulse here. When I am giving a 16th clock pulse, this value, instead of getting incremented, now it gets decremented, and it goes down for binary 14, binary 13, binary 12, and so on until binary 0, and once 0 reaches, from there it starts counting up again. We will see the graphs anyway. From there it starts counting up. So this is one possibility. This is the first possibility. And the second possibility is we are having all zeros at first. I am giving the first clock pulse, so this bit alone gets changed to 1. I am giving the second clock pulse, so this bit changes to 1 0, and so on. It will keep continuing up to 15, just like the previous case. 15th clock pulse will be recorded. After that, when at 15, what will be the value showed here? It will be all ones. After 15th clock pulse, all ones will change. If we give the 16th clock pulse now, it will change to all zeros. Everything will become 0 again. And when you give the 17th clock pulse, again it will start counting. This will become 1. So this method is called up-down counting. And the second method, which we told just now, is called up counting. To visualize this up counting and down counting, what they usually do is they draw a graph, which may look something like this. On the x-axis, you will have time, and on the y-axis, you will have value stored in the register. This will be across your y-axis. Now, at the first microsecond, what was my value in the register? It was 0, 0, 0, 1. At 0th microsecond, it was 0, all 0. At the second microsecond, what was the value? The value was 0, 0, 1, 0. At the third microsecond, my value was 0, 0, 1, 1, and so on. Arduino actually inherently has the capacity to address numbers in decimal, because human beings are more comfortable with decimal number system. Even if you equate a decimal number to a register, it will convert it into a respective binary and store it. So let us, for understanding purpose, talk in terms of decimal itself. So this is 0, this is 1, this is 2, and this is 3, and so on. At the 15th microsecond, and this is time in microsecond, at the 15th microsecond, it will reach value 15. So your visual representation will look something like this. Dot, dot, dot. On the 15th microsecond, this will become 15. Now, if it is up counting only, not down counting, then at the next clock pulse, it will come down. And for 16th, it will again go up like this. This is what we call as a discrete sawtooth waveform. So this is very much like a sawtooth waveform, and which is achieved by counting action. This is what we call as a discrete sawtooth waveform. Now if you do up-down counting, then your process will be something like this. We'll have the x-axis here, we'll have the y-axis here. It will keep counting up to the maximum value, and then from the 15th microsecond, after 16th microsecond, it will come down. It will come down and settle here, and again it will stop counting. So this will give you a triangular wave structure, and up counting will give you a sawtooth wave structure. Now what is the frequency of this sawtooth wave? That's the next thing we have to see. The frequency of this sawtooth wave is 1 upon its time period. The time period of this sawtooth wave is 15 microsecond. So T sawtooth equals 15 microsecond. So what will be F sawtooth? It will be 1 upon T sawtooth, which is 1 upon 15 microsecond, which is 66.67 kilohertz. This at this frequency of 66.67 kilohertz, you are getting a sawtooth waveform. Now, I am interested to get some other frequency other than 66.67 kilohertz. So what I will do, I will tell my microcontroller to not stop counting at 15, but to stop counting at 10 itself. So the moment I ask it to stop counting at 10, let me write this. I am telling my microcontroller to stop counting when you reach value 10, which is 1010. I'm telling this to my microcontroller. So if I tell this, my microcontroller will stop counting at 10. So 10 may appear somewhere here roughly. So once it reaches 10, it will come back to 0, and then from 11 it will start counting like this. And again it will reach 10, it will come back, and from here it will start counting like this. Now you could see that the frequency of this sawtooth wave will be F sawtooth equals 1 upon, here your T sawtooth is no longer 15 microsecond, your new T sawtooth is 10 microsecond. So this is nothing but 100 kilohertz. So your F sawtooth is now 100 kilohertz. Now we got a frequency sawtooth waveform of 100 kilohertz. Now you should notice that the amplitude has reduced. Doesn't matter. You will understand later why it doesn't matter. So this is how we produce sawtooth waveforms of different frequencies. So what are we doing? We are deciding up to what value it should count. So we store this data in a separate register called as a period register. So this, when I am saying that stop, when you reach this value, you stop counting. When I say this to my microcontroller, this value is actually stored in another register. So those details are going to be explained next. So basically this is my counter register. My counter register gets updated at every clock pulse. So this register is going to be updated, keeping on, it's going to be updated. And there is another register called as a period register, which decides my top value of the sawtooth waveform. So what am I storing here? I am storing value 10 here. Here I am not going to store any value. It is not under my control. For every clock pulse, it's going to increment itself. And also, I am telling my microcontroller to do up counting. Don't do up down counting. To produce sawtooth waveform, do up counting. So this is another instruction I am telling my microcontroller. This may seem absurd now. Please wait till the end of the video to see what's actually happening in the background. Now, when I input such a value, that's how this phenomenon takes place. So this counter value starts from all 0. It will start counting from 1, 2, 3, 4 and so on, 5, 6, 7, 8, 9, and when it reaches 10, my counter register contents matches with the period register. So once this matching happens, so basically it keeps counting, right? So it keeps counting from 1, from 2 and so on. And once this reaches maybe 1001, this is number 9. So it has reached up to number 9. And the moment it reaches 10, the next clock pulse comes in, and when it reaches 10, this will reset again to 0. So at what value should I reset again to 0 is stored in my period register. So the top value of my counter is decided by the period register, and that obviously determines the period of this sawtooth. If I'm storing higher value, you are allowed to count up to this point and then come down, so you'll have a larger sawtooth period. If you are stopping at a early value, you will have a smaller time period, and time period, you know how it's related with frequency, it's inversely related. So this is how this period register works. Now I have produced my sawtooth successfully. The next part is having a duty ratio to produce a PWM. So this is how my sawtooth will look like. My next part is to generate a duty ratio such that I am able to produce my PWM. So for generating the duty ratio, we use a register called as compare register. Why is it called a compare register? Because this register is going to be compared every time with your counter. The moment these two become equal, something is going to happen. So now my duty ratio value should go and sit here. Now you may ask, my duty ratio lies between 0 and 1. Basically, how am I going to convert this into this? Just understand something. If whenever you are having a sawtooth waveform, the amplitude, and when you are using this for producing duty ratio, and when you say my duty ratio should lie between 0 and 1, it simply means that your sawtooth is varying between 0 and 1. But here my sawtooth is not varying between 0 and 1. My sawtooth is varying between 0 and 15. So 1 here corresponds to 15. That means what? This duty ratio is going to vary between 0 and 15 in integer system. Okay. So my compare register can have a value between 0 and 15. When this is having a value of, I'm sorry, this is not 15 here, this is 10. This value is 10. So basically, let me repeat again, when I'm saying that my duty ratio essentially lies between 0 and 1, and here I'm producing a sawtooth whose counter value is varying between 0 and 10, my duty ratio basically varies between 0 and a scale of 10. Everything is amplified now. It's between 0 and 1, everything is amplified between 0 and 10. If you're having 800 steps, you have to scale your duty ratio according to 800. So 0 corresponds to 0 and 1 corresponds to 10 here. That means what? When I'm talking about a duty ratio of 0.5, I mean to say a number 5 here. So I will store, to produce a PWM of duty ratio 0.5, I will store a value 5 here, which is 0101. I will store this fixed. This is not going to change. If my duty ratio is not going to change, this is going to be fixed. Now this counter keeps on changing. Again, period register is a fixed thing. This decides your frequency. So it should be just like that fixed. Now I have stored a value here. So now my counter starts counting from here. It's count from 0, 1, 2, 3, 4. The moment it reaches 5, yes, there's a compare match. This is called a compare match. This and these are equal, basically, because it's counting up to 5. Now my value here will be 0, 1, 0, 1. Both are equal. Since both are equal, it will change my pin. Some pin corresponding to production of PWM from logic 1 to logic 0, and then it will keep it here, and then it will keep counting again. 6, 7, 8, 9. When it reaches 10, it will see now this value, my counter value is 10, 1010. These two are matching, so it will stop there. and then it will be reset to 0. Whenever my counter value is resetting to 0, automatically this should go up. I will tell my microcontroller that this PWM pin's output should go up and stay up until what time? Until next time 5 reaches. Until next time this 5 reaches, this is my duty ratio basically. This is my duty ratio, and this value is stored in my compare register. When 5 comes, I will say, okay, you go 0. You go to 0 and stay in 0 until next period comes. Next period register match comes here, next period register match comes here, next compare match comes here, next compare match comes here. So this is how I produce a duty ratio of 50%. So on a bigger picture, you might have noticed me saying, I will tell my microcontroller to do this way. I will tell my microcontroller to do this way. So this is the pin. I've just drawn it for graphical or for representation. So this is my PWM pin. So this pin will be held to 1 or 0 based on these conditions. Now I have to instruct my microcontroller operate in this particular fashion. There is another way to operate, isn't it? Initially my pin could have been 0, and when this compare match comes, it could have risen up to 1. And up to the next period match, it could have stayed at 1. And when the next reset comes, it could have come to 0. Basically, you will get a complementary signal to this. This kind of thing is also possible, but I am communicating to my microcontroller, do this. I am communicating to my microcontroller that whenever your compare register, which is this register, is greater than your counter, I want a PWM, I want a logic high in my PWM pin. On the other hand, whenever my compare register is lesser than my counter, other way around, whenever it is lesser, then make this pin 0. Make this PWM pin's logic 0. I am telling my microcontroller this also as a rule. So there are many things which I am saying my microcontroller that you should operate in this particular fashion among all these fashion. So whatever instructions I am telling on how to increment the value or how to decrement the value or how to operate these registers associated with timers and counters, these information will be stored in another register called as timer control register. In Arduino, we have this as TCCR, timer counter control register. This is again a register. It may have some zeros and ones. If you write zeros and ones, see in the data sheet, if you write zeros and ones accordingly, then you can make it follow this rule. And if you write in some other combination, you can make it follow this rule also. Then if you add some other ones and zeros appropriately, you can make it follow this rule also. You can make it function in a certain way that you want it to function among all the possible ways. So that is the usage of timer control register. With this, we have covered the basics of how PWM signal for a DC-DC converter is produced using any microcontroller. To summarize, we have seen 4 registers. Basically, one is counter register, another is period register, the third one is compare register, the fourth one is control register. Counter registers keep incrementing with every clock pulse. Period registers determines the time period of sawtooth, and compare register will determine the duty ratio. So when you deploy a closed loop system, this duty ratio will be computed every time and it will be updating. So this whole thing may move up and down depending on the conditions of the system. And the control register is used to configure your timer. With that, we can conclude this video.